So now we get to go into molecular orbital theory, which is the theory based on quantum mechanics I've been talking so much about, and is really the best reflection of reality for how bonding, structure, and dynamics of all compounds in chemistry work. Okay, and so we abbreviate this MO theory. The idea here is now we know about atomic orbitals, so we're going to add the wave functions of two or more atomic orbitals together to form what are called molecular orbitals. And we know that waves can interact constructively or destructively. When we have the wave functions of two atomic orbitals interacting constructively, these are called bonding orbitals. That is, the waves add up. Okay. When they are out of phase, then you have a calm, right? The two waves hit each other and kind of no motion in the water afterward. So that's a destructive interference. And when two orbitals add up in that way, that is called, and those are called antibonding orbitals. If two waves sort of just kind of go past each other, usually this is because they have the wrong symmetry. This is called non-bonding orbitals. Okay, non-bonding orbitals. So this is just sort of a schematic of this, what we said. Take the example of two 1s atomic orbitals, and you have some wave functions depicted by simple two-dimensional waves here. And what happens is you can have constructive interference to make a bigger wave. That would be like a bonding molecular orbital, or destructive interference where you have an anti-bonding orbital, and you're going to have then a node somewhere where there's not any electron density, zero probability. So what are the different ways that you can add two atomic orbitals? Well, you can add them in bonding ways. Basically, any permutation of different types of atomic orbitals can work as long as there's the right symmetry for overlap. So what you'll see what I mean by that. So a p orbital can interact with an s orbital. Of course, here was two s orbitals. That can also work. But if the same phase is the correct phase of the lobe of one of the p orbital interacts with the same phase of the s orbital, that's going to be a bonding interaction. Two p orbitals with the correct phases lined up, dark with dark. A d orbital lined up with a p orbital, dark with dark there. Here are two p orbitals going side on, right? And we have dark to dark on the top, light to light on the top. That's going to be constructive bonding interaction. A d orbital and a p orbital side on. Again, dark to dark, light and light. That's going to be constructive. Two d orbitals side on, dark to dark, light to light. Exact opposite situation for antibondings, where you have now opposite signs, dark and light interacting. That's going to give destructive interference and give rise to antibonding interactions. So for all of these bonding interactions that we drew on the left here, we can draw sort of the equivalent opposite type of interaction, which would be an anti-bonding interactions. Non-bonding interactions are kind of interesting. Here's where you have like the wrong symmetry. And so it's neither constructive nor destructive. There's actually no interaction. And so consider, for example, this p orbital oriented like this with this s orbital. The top half is going to be dark to light, but the bottom half is dark to dark. So dark to dark. So the top half is destructive. The bottom half is constructive. Net, it's nothing. Same with this one, two p orbitals with the wrong symmetry. Very similar idea here with a d orbital side on to an s orbital, or the dz squared orbital with a p orbital. How does this one work? Well, top you have constructive, right? Dark to dark lobes. Bottom you have destructive, dark to light lobes. And then in the middle you have a light colored donut, right? But that's equally interacting with the dark top lobe of the p orbital, destructive, as it is with the constructively interacting with the light bottom lobe of the p orbital, constructive. So the donut interactions effectively cancel out to nothing. So this is also non-bonding.